So for a few years now you've been talking about the nucleus, but nobody's really explained to you how it is possible for a nucleus to form. It seems totally illogical, doesn't it? You might have remember a little bit about the plum pudding model from GCSE, where Rutherford was very surprised that the protons would all be stuck together, when the one thing we know about protons is they've all got the same charge, so they're all repelling each other. So we need to look at this force, the strong nuclear force. This is the force that holds the nucleus together. So it's got to overcome all that repulsion of all the positive things being in the same place. So we've got to look at the forces in the nucleus. We've got to talk a little bit about their relative sizes. And then crucially, you need to learn the key features of the strong nuclear force. You might think you know quite a few forces. You might think about friction and air resistance and all those kind of forces. But actually, if you break it down, all those forces come down to either being gravity, or they become the repulsion of the electrons on the outside of things, or they become the attraction between the protons and the electrons. That's how atoms are held together. Right, so friction, for example, is just the electrons in one thing repelling the electrons in the other thing and pushing them up, and you have to put in some force to make them bounce over each other. That's why smooth things have less friction. Right, so all those forces that you might think you know, if you break them down, at the moment you only actually know two different forces. Okay, so here's two protons to stick them together. At the moment, if we only know forces of gravity and what's called the electrostatic force, or sometimes Coulomb repulsion, this is just a force because they're both positively charged. Right, there's an equation that Newton worked out for the force between the force between two masses. This is a constant. You multiply the two masses together, you divide by the distance squared. Well, the two protons in a nucleus are about 10 to the minus 15 metres apart. Their centres are 10 to the minus 15 metres apart. So we can just plug all the numbers in. We know the masses of the protons now, 1.66 times 10 to the minus 27 kilograms each. We know the distance here, 10 to the minus 15. If you plug all the numbers in, then you find the attraction of those protons is 1.86 times 10 to the minus 34 newtons. Okay, and then this French guy, Coulomb, worked out the equation for repulsion, and he's got another constant here. Multiply the charges together. Again, we know the charges now is 1.6 times 10 to the minus 19. Plug in the distance, and we get 2.27 times 10 to the 5 newtons. So if I was to say to you that gravity is holding it together and the electrostatic repulsion is pushing it apart, it's pretty clear, hopefully, which one of those two forces is going to win. This force is 10 to the 39 times. That's 1,000 million times bigger. So there's no way that gravity is holding the nucleus together, because the only force that really has any effect on these two things that we know already is the electrostatic repulsion. Think about the size of that force. That's a big force on a human scale. This has been applied to a tiny proton. Okay, for example, if we wanted to work out the acceleration, we do the force divided by the mass. This would create an acceleration of 1.4 times 10 to the 32 meters per second. If you applied that force for 10 to the minus 24 of a second, it would already be travelling at the speed of light. So there must be something else. Well, there's something else we've already said. It's called a strong nuclear force. It must be strong, okay, because it's got to overcome this huge force of electrostatic repulsion, and it happens in the nucleus, and it's a force. So strong nuclear force, sometimes just SNF. Okay, some things that we can work out for this. It must have a short range. If it hadn't got a short range, then the nucleus could just get bigger and bigger and bigger. And also it must act between all nucleons, because otherwise the neutrons, which we haven't mentioned yet, but the neutrons wouldn't be held into the nucleus. So here's our first two key facts about the strong nuclear force. Okay, we can have a look at those two facts, and that will give us an idea to why there's a limit to how big the nucleus can be. Right, this is a simplification. Okay, obviously the nucleus isn't a 2D structure, it's a 3D shape, and also the forces change a lot with distance, but you might be able to just see the basics. So this little dotted line around here, this is a kind of rough idea of the limit of how far the strong nuclear force acts. So if we've got a small nucleus, right, all these particles, these 5 particles here, they're all attracting this proton which is at the edge. How many are repelling it? Well, the neutrons aren't repelling it because they're neutral, they've got no charge. Only these two are repelling it. So I've got 5 things attracting it, 2 things repelling it. This should be a nice stable nucleus. This is a lithium-6 nucleus. Okay, there's no way this proton's going to get pushed out of that nucleus. It's being quite strongly pulled in. All the things are pulling it in. Once the nucleus gets a bit bigger, right, then what happens to the number of particles attracting it? Well, it's only gone up to 1, 2, 3, 4, 5, 6, 7 that are inside this circle close enough to pull this proton. So we've got 7 pulling it. How many are repelling it? Well, again, we count the positive charges. 1, 2, 3, 4, 5, 6, 7, 8 repelling it. Is it stable or not? Yes, it actually, even though 8 is bigger than 7, you might think, oh, no, it's not. These ones are a lot further away, and we haven't really talked about the size of the forces too much. But it might give you the idea that it's starting to become less stable. Eventually, I haven't managed to draw all these, but imagine this nucleus is getting bigger and bigger and bigger. The number of particles that's attracting this proton isn't getting any bigger, so there's still 7, however big the nucleus is. This one on the edge is only being held in by the ones that are close to it. Right, once you get to the stage where there's maybe 80 protons in here, I haven't drawn anywhere near 80, but if there's 80 protons in there, now we've reached an atomic number around 83 somewhere. We've already said that 83 is the biggest atomic number you can have. Any bigger than that, right, what starts to happen is you get a little group of particles, so 2 protons and 2 neutrons. So here's a little group. This little group might get pushed out altogether, and that's an alpha particle. That's alpha decay. Okay, so a little bit more detail on the strong nuclear force. Here are the facts. You just have to learn these facts. Hopefully they'll make a bit of sense to you. But if they ask you to quote them, you need to be able to quote these. So it acts between all nucleons. Once you go past about 3 femtometers, I should mention this, femtometers, a little f, this is 10 to the minus 15 of a meter. So you go meters, millimeters, microns, nanometers, picometers, and then you're down to femtometers at 10 to the minus 15. It's attractive from below 3 femtometers down to about half a femtometer, but once you get down to half a femtometer, the force actually becomes repulsive. Okay, we can work out why that is, because if it didn't affect neutrons, right, then the neutrons would not be held in. All the protons would get pulled together into the center of the nucleus. The neutrons would be around the outside. They just kind of float off. If it had a bigger range, so this is the kind of size of an atom, 10 to the minus 10 meters, if the strong nuclear force was that big, you'd end up with a huge nucleus. So you could get a nucleus with thousands and thousands. The chemists would be going mad because the periodic table would be much, much longer. Right, the reason that the periodic table finishes around atom number, well, 83 in terms of stable atoms, right, is because that's as big as you can get before the protons on the other side are pushing too hard for the proton on the opposite side to stay in. Right, if it didn't become repulsive at small distances, this is the one that we've just snuck in on you there. So if it didn't become repulsive at small distances, then basically matter would just collapse. So eventually you get to the stage where protons and neutrons would just collapse in on themselves, and the nucleus would form into a tiny little black hole at the centre of an atom. Okay, we can show this in a sort of graphical form. So we've got our graph here. I've already put one number on there, 220 kilonewtons. Remember we said 227 kilonewtons was the force between 2 protons of repulsion. We've got to overcome that force. Okay, here's our distances that we just mentioned on the last slide there, half a femtometer, 1 femtometer, 3 femtometers. This is the separation. So notice on this graph, if we're in the top half up here, then the force is repulsive, so it's pushing them apart. If we're down here, it's attractive. What forces do we know? Well, we've got the electrostatic repulsion. Okay, that decreases with distance. Okay, in a way that we'll look at in detail in A2, but when you're at 1 femtometer, okay, it's here. If you're at 2 femtometers, it's actually a quarter as strong. So a curve something like this. We've got the strong nuclear force. Well, remember all the things that we've just said about this. Below half a femtometer, it's repulsive. Okay, once you go past half a femtometer, it becomes attractive, down to about 1, where it's most attractive. And then once you go past about 3, then the force becomes very, very small. And then what's important, of course, is the overall force, the resultant force. So if we draw the resultant force, then the graph looks something like this. Okay, notice there's a key feature here. At about 1 femtometer, the resultant force is 0. That means at 1 femtometer, the nucleus, the separation will become stable. If you move closer than 1 femtometer, the force becomes repulsive. So they get pushed back towards 1 femtometer. If you move further away than 1 femtometer, then the force becomes attractive. They get pulled back together again. So if you start from here, if you move away, you're going to get pulled back to that point. Okay, it's interesting to note that this point is not stable, because if you drift slightly further apart than 3 femtometers, the force becomes repulsive and moves you even further apart. If you become attractive, it becomes even more attractive and you get pulled together till you come here. Okay, so these are the key features of the strong nuclear force. What we need to know is that this is why the nucleus can stay together, and we need to learn those key facts on the slide before.